In Chapter 10, we want to look at thermodynamics and thermochemistry. Thermochemistry will be our chance to look at heat, temperature, entropy, enthalpy, Hess's law, and calorimetry type problems. Let's start with a quick review of some of the stuff we've talked about in class dealing with heat, energy, and temperature. Energy is the ability to do work or produce heat. And with energy, there are lots of different types. We have potential energy based on the position or composition of an object. We're going to generally look at composition for potential energy in chemistry. Kinetic energy based on the motion of an object. So this will be related to temperature. There's all other types of energy that exist, many others such as thermal energy, nuclear energy, and many other types. But we're going to really try to focus on the idea of conservation of energy and heat and temperature. The law of conservation of energy states that energy can be converted from one form to another, but it cannot be created or destroyed. There is a set amount of energy available. That energy cannot be created from any new source. That energy cannot be destroyed and got rid of. It can just be converted from one form to another. Temperature is one of the main things that we deal with in this class. Temperature is a measure of the random motions of the components of a substance. So how fast the particles are moving. Now understand that some particles are moving faster, some particles are moving slower, and we find sort of an average of the movement of the particles to determine temperature. If you were actually to do a graph to look at temperature, if you had the velocity, the number of particles versus the speed, you kind of see a bell-shaped curve. And the average, about the middle, would be where we'd set the temperature. There are going to be some that are moving faster, some that are moving slower, but the majority will be moving around this middle speed. Higher temperature would mean more of the average moves up to a higher speed. Heat is a little bit different than temperature. Heat is the transfer of energy from a warm object to a cold object. So when particles are moving fast, transferring that energy to slower moving particles, causing the faster moving particles to slow down and the slower moving particles to speed up until they come to a common temperature. Now when we have changes in energy, we have to define a couple of things. First, we have to define the system. The system is the specific part of the universe that is of importance to us in this reaction. Generally, it's going to be the chemical reaction we are looking at, or the chemical process we are looking at. Surroundings are going to be everything else in the universe. So if energy is transferred into the system, or out of the system will change the type of reaction we are dealing with. Now, there are two types of reactions when it comes to energy, exothermic and endothermic. An exothermic reaction is a reaction where energy is being released by the system. So the system, the reaction, is giving off energy. These are the reactions that feel very warm to us. They are exothermic reactions. Burning something is an exothermic reaction. The system loses energy, the surroundings gain that energy, and you feel the heat being given off because the warmer system is losing energy to the surroundings. Endothermic reaction, energy is being absorbed by the system. These are the reactions where the container would feel cold. And chemical ice pack, when you break the chemical and shake it around and it feels really, really cold, that's an endothermic reaction. The system gains the energy from the surroundings. One thing that is always true is that for any energy that is being lost by this or gained by the system must come from the surroundings and vice versa because of the law of conservation of energy. Now, thermodynamics, the first law of thermodynamics is that the energy of the universe is constant. This is that law of conservation of energy. To measure energy, one of the things we use is the SI unit, that is the joule. We also use the unit of calories, so joules and calories. 1 calorie is equal to 4.184 joules. This is an important value to know here because this is our conversion between calories and joules. We also have food calories, and food calories, capital C calories, are kilocalories. So there's 1,000 calories in a food calorie or kilocalorie. Now, the first type of problem we want to look at is dealing with specific heat. When you are having a substance change its temperature is based on 3 factors: the amount of energy, the mass, and what's known as the specific heat. So the heat transfer depends on those 3 factors: the capacity of a substance to absorb heat, which is known as specific heat. Some things absorb heat better, some things absorb heat not as well. Think of metals. Metals particularly absorb heat very easily, whereas other substances do not absorb heat very well. Its mass and its change in temperature. And that gives us the equation Q equals ms delta T, where Q is the amount of heat that's being transferred, the amount of energy that's transferred from the warm object to the cold object, and M is mass, S is specific heat, and delta T is change in temperature. So specific heat, the S, this is the definition right here. So this is our definition. So specific heat is defined as the quantity of heat needed to raise 1 gram of a substance by 1 degree Celsius. And that is the variable S. So whenever we think of specific heat, we're looking at that variable S. The units for specific heat are either joules per gram degree Celsius, so the amount of energy divided by the grams and the change in temperature. Think about the equation. If you were to rearrange the equation to get S by itself, you would do S equals Q divided by M delta T. So Q is in joules or calories, M is in grams, delta T is in degrees Celsius. Now let's look at some sample problems. Gold has a specific heat of 0.129 joules per gram degree Celsius. How many joules are required to raise the temperature of 15 grams of gold from 22 to 85? So our equation here, Q equals ms delta T. So our mass, 15 grams. Our specific heat, 0.129, and our change in temperature, final minus initial. So to figure this out, we need to do 85 minus 29, which is 56. Multiply that by 0.129, and then multiply that by 15. And we get 108.36 joules. And now, based on significant figures, we had 2 significant figures, so our correct answer, 110 joules. Second problem, an unknown substance with a mass of 100 grams absorbs 1,000 joules while undergoing a temperature increase of 15 degrees Celsius. What is the specific heat? So here we're solving for a different variable. So Q equals ms delta T, 1,000 equals 100 S times 15. So 1,000 divided by 100 divided by 15 gives us a specific heat this time of 0.67 joules per gram degree Celsius. And the third problem here, copper has a specific heat of 0.385. A piece of copper absorbs 5,000 joules of energy and undergoes a temperature change from 100 to 200. What is the mass of the piece of copper? So Q equals ms delta T. 5,000 equals the mass, which we're trying to find, the specific heat, 0.385, and a change of temperature of 200 minus 100. So divide 5,000 by 100, then divide it by 0.385, and you get 129.87 grams. The mass, 129.87. The 5,000 joules, technically one significant figure here. I would treat that as exact. Let's keep the 3 significant figures here. So 130 grams. Put the decimal point at the end to keep the 3 significant figures. So those are examples of specific heat type problems in which we're using the equation Q equals ms delta T. M is mass, S is specific heat, and delta T is change in temperature.